Let's find coordinates of in center of triangle when vertices of triangle are given. First of all, what is in center of triangle? We can inscribe one circle inside triangle which touches all the three sides of triangle. In center is center of that triangle. So this is circle inscribed in triangle. So let's circumscribe triangle outside. Okay, now center of this circle is called in center and this circle is in circle of triangle. This is in radius small r of triangle. At in center, internal angle bisector of triangle are also concurrent. So if we join vertex A to this in center, then this line is angle bisector of A. Similarly, if we joined B and I, then this line BI is angle bisector for angle B. And similarly, if we join C and I, we have this CI line which is internal angle bisector of angle C. So at in center, internal angle bisectors of triangle are concurrent. Also, it is center of in circle which touches all the three sides of triangle. Now, in center of triangle always lies inside triangle, whether triangle is acute angle, obtuse angle or right angle. Let's see one important geometry related to in center, or in fact angle bisector of triangle. Consider one acute angle triangle ABC. Let's draw angle bisector BE. Now, there is one important geometry about this angle bisector, and that is this angle bisector divides side AC at point E in the ratio which is AE upon EC, which is given by ratio of adjacent sides, that is AB upon BC. For example, if we draw angle bisector for angle A, then this bisector divide opposite side BC in ratio which is BD upon DC, which is given by ratio of adjacent sides of triangle, that is AB upon AC. So let's prove this fact. Let's draw one line parallel to line BE from vertex A. Extend BC. Suppose this extended side BC and the line parallel to B from vertex A intersect at point D. Now, angle DAB will be equal to angle ABF. Okay, these two angles are same. If we mark this, then this angle and this angle are equal. Okay, further, since this line and this line are parallel, this angle and this angle are also equal, so we have these two angles equal. So triangle ABD is isosceles triangle. So we have BD is equal to AB. These two sides are equal. Now, since these two sides are parallel and these angles are equal, triangle BCE is similar to triangle DCA. Then we have EC upon AC is equal to BC upon CD, or EC upon, what is AC? AC is sum of AE plus CE is equal to BC upon, what is CD now? CD is sum of BD and BC. But we have already proved that this BD is equal to what? AB. So in this, replace BD by AB. So we have EC upon AE plus CE is equal to BC upon AB plus BC. Now using property of ratios, we have EC upon AE is equal to BC upon AB. We have this property, A upon B is equal to C upon D. Then we can go for A upon A minus B is equal to C upon C minus D. So here we are subtracting numerator from denominator both sides. This is one of the properties of ratios. So we have proved that EC upon AE is equal to BC upon AB. That means angle bisector of B divides opposite side AC in the ratio of adjacent sides. Adjacent sides are AB and BC. Using this property of angle bisector, we can get coordinates of incenter. Consider triangle ABC with vertices x1, y1, x2, y2 and x3, y3. In this triangle, using standard notations of sides, side length opposite to angle A is small a, side length opposite to angle B is small b, and side length opposite to angle C is small c. Now we want to find coordinates of incenter. For that, let's first target point D. How we can find coordinates of point D? Now D lies on BC. We have coordinates of B and C. So we can get coordinates of point D if we have ratio BD upon DC. Just now we proved that BD upon DC is equal to what? AB upon AC, that is small c upon small b. Now we have ratio BD upon DC and coordinates of B and C. Then we can get coordinates of point D using section formula. So using section formula, coordinates of point D are B will multiply with B and C will multiply with C. So we have bx2 plus cx3 upon B plus C, comma by2 plus cy3 upon B plus C. So we got coordinates of point D using section formula. Now to get coordinates of I, we will consider line AD. In this AD we have coordinates of A and D. So if we want to find coordinates of point I, we should have ratio AI upon ID. How you get AI upon ID now? If we consider triangle ABD, this triangle, in this triangle BI is angle bisector. Then in triangle ABD we have AI upon ID is equal to what? AB upon BD. Using same property of angle bisector, which divide opposite side in the ratio of adjacent sides, that is AB upon BD. Now AB length is small c by notation, but what is length BD? We don't have length BD, so we have to first find length BD. Any idea how we find length BD? We have ratio BD upon DC, that is C upon B. So length BD is equal to CK and length CD is equal to BK. Now if we add BD and CD, so their addition will be K times B plus C. And what is BD plus CD? That is length BC or small a, from which we have value of K. So value of K is A upon B plus C. And if we put this value of K here, we have BD is equal to AC upon B plus C. So in this ratio AB upon BD, we have C upon AC over B plus C, that is B plus C upon A. So we have now ratio AI upon ID, which is B plus C by A. Now we have vertex A, coordinates of D, and ratio AI upon ID. So we can get I using what? Section formula. So let's draw one different diagram for A, I and D. This is A, which is x1 comma y1. Here it is D, which is this. Okay, now I is somewhere here, and this ratio AI upon ID is B plus C upon A. So coordinates of I will be A will multiply with A and B plus C will multiply with D. So using section formula, coordinates of I are A times x1 plus B plus C times abscissa of D. Similarly, we have y coordinate. Simplifying, we have in center ax1 plus bx2 plus cx3 over a plus b plus c. Similarly, y coordinate, that is ay1 plus by2 plus cy3 upon a plus b plus c. So if vertices of triangle are given, we can find in center, where A, B, C are what? Length of sides opposite to angle A, B and C. Find in center of triangle having vertices 1, 2, minus 2, minus 3 and 2, 0. To get the in center, we have to first find side length of triangle. Side length, this one is square root of 9 plus 25, that is square root of 34. This side length is square root of 1 plus 4, that is root 5, and this side length is 16 plus 9, that is 5. Then in center of triangle is, by formula, abscissa of A will multiply with side length BC, and we have 5 multiplied by 1 plus root 5 will multiply by minus 2 plus root 34 will multiply with 2, and in denominator we have sum of sides, that is 5 plus root 5 plus root 34. By similar pattern we can get y coordinate, which is 5 multiplied by 2 plus root 5 multiplied by minus 3 plus root 34 multiplied by 0 upon 5 plus root 5 plus root 34. So these are coordinates of in center. So to get in center, we have to get all the side lengths, and then we can use straight away formula ax1 plus bx2 plus cx3 upon a plus b plus c. Similarly, y coordinate, which is ay1 plus by2 plus cy3 upon a plus b plus c. Since to get in center we have to get side lengths, and here we can see that in center has irrational coordinates. So if all the vertices of triangle are rational, or all the vertices have rational coordinates, what do you understand by rational coordinates? That is, all abscissas and ordinates are rational. Here in fact all the points have integral abscissas and ordinates. Okay, here though all the vertices have integral coordinates, in center is irrational. This is because to find in center we have to get side lengths, and side length can be what? Irrational, because we find side lengths using what? Distance formula, which involves square root. It is not necessary that when the vertices are rational, in center is always irrational. It may be rational, but we can say that when vertices have rational coordinates, in center not necessarily rational.